Hello again, everyone. Today we're going to go on to the next lesson in our oxidation and reduction reactions unit. So far we've worked on assigning oxidation numbers. So we're going to do a quick practice of that. So take a look at this do now. The worksheet's attached to this lesson. So take a minute and let's try these on our own and review what we've been doing. So I'll do the first one with you. So remember how to do these. So you want to assign oxidation numbers, meaning every element in the compound gets an oxidation number. So remember how we do that. The whole thing's always got to add up to 0. So make your little table and use what you know to figure out what we don't know. So we're using our rules. So remember, go by the periodic table as well. So we know our rules that we went over. Group 1s are always +1. Group 2s are always +2. Fluorine's always -1. Oxygen's usually -2. Hydrogen is usually +1. But then also just use your periodic table. Remember, if an element only has one oxidation state, most likely you can use that to help you out. So here, number one, what do we know? Well, calcium is a group 2, so we know that it's +2. So now we get our total on the bottom. +2 times 3 is +6. So remember, we got our totals on the bottom down here. And remember what I kept saying before, you want to kind of multiply your way down. So you take the oxidation state times the number of atoms in the compound, and that gives you your total. So totals on the bottom, individual oxidation states go up top, and that's what you want for your final answer. Every element needs an oxidation state. So what do I need to get to 0? I need -6. So there's 2 phosphoruses. So remember, we divide our way back up. So we multiply down, divide up. So -6 divided by 2 means each phosphorus gets a -3 charge. So we're done. So that's what we're going to use to move on in the next part of the lesson today. But if you can do that, you're doing great. So pause the video, take a minute, work through the other problems here, and then unpause it, and we'll see how you did. All right, so let's go through these. Number 2 now. Don't forget, this is the first rule that we went over when we did all these rules. Uncombined elements get a 0. So if you gave fluorine a -1 here, that was a mistake. That's only for when you're dealing with compounds. When fluorine is in a compound, when it's bonded to multiple different elements, then you're going to follow those other rules that we went through for when we're dealing with bonded elements. Here, we consider this an uncombined element. Even though it's 2 fluorines stuck together, they're atoms of the same element, so we still consider that their elemental states. That's one of our Brinkelhoffs. So gets 0. Don't forget that. If you mess that up, that's going to make a lot of issues going forward in this topic. Next one, break it up. Right? There's 3 elements, so we need each element to have an oxidation state, regardless of polyatomics or not. Everybody gets an oxidation state. Use what you know to figure out what you don't know. So we knew oxygen and we knew hydrogen. So we're figuring out sulfur. Sulfur gets +4. Next one, this is a good example because you don't want to stop too early here, right? So we knew calcium, we knew oxygen. So we ended up with -12 before filling in the middle here. So that tells us we needed a +12 to get to 0. But you don't want to stop there. If this were like a multiple choice question, one of the choices would probably be +12. Because you go, oh, I got it equal to 0, it's +12. Don't forget to distribute it amongst all of those chromiums. So there's 2 chromiums. So +6 divided by 2, or +12 divided by 2 means each chromium gets a +6. So now you're done when every single element has an oxidation state. And you'll see how that plays out as we go into today's lesson. All right, number 5. This is a good example of our rules. Always, sodium's a group 1 element on your periodic table. Always +1. Hydrogen is usually +1. So this is an example of where always overrides usually. So sodium wins, hydrogen adjusts and becomes -1 because that's what we need to equal 0. Next one, number 6. There we go. Don't forget about your parentheses, right? That 3 applies to everything inside the parentheses. So 3 times 4 means there's 12 oxygens and 3 sulfurs. So you got to account for that when you're totaling up your thing. So minus 2 times 12 is negative 24. Aluminum, remember, we don't have a rule for, but it only has one choice on the periodic table, so we go with that. So it's plus 3. Plus 3 times 2 gives me plus 6. So what do I need to get to 0? I need 18 more. So I need a positive 18. But don't forget to distribute that amongst your sulfurs. There's 3 of them. So 18 divided by 3 means each sulfur gets a plus 6. Now, number 7, this is one where it doesn't add up to 0 because we see that charge in the top right. So that's always going to be there, right? That's going to start out there. You're not putting that there. So that minus 2 in the top right corner is telling me this whole compound has a charge. So that means we're dealing with a polyatomic ion. So it's not neutral. It adds up to minus 2. So when we set up our table, it's going to add up to that charge. That's all. Other than that, they're always going to add up to 0. So we know oxygen, it's negative 6, but now we only got to get to minus 2. So we need a plus 4 to do that, and then carbon gets the plus 4. Now, number 8's a tricky one. This is a peroxide, and this showed up on yesterday's worksheet as well. So this is a peroxide. This is hydrogen peroxide. So in this case, oxygen is the one that adjusts. So oxygen, according to our rules, is usually minus 2. Hydrogen is usually plus 1. So if that's the case, how come I couldn't do it like this? Right? How come I couldn't make oxygen minus 2? Minus 2 times 2 is negative 4. I got to get to 0. So I need a plus 4. So why can't hydrogen be the one that adjusts and becomes plus 2? Works out mathematically, it still gets me to 0. So if you got that as your answer, that's a common answer that's given, but let's think about why that's not correct. All right, hydrogen. Think about your structure of a hydrogen atom. Hydrogen has 1 proton, its atomic number is 1. So as a neutral atom, it has 1 electron. So what does this plus 2 imply? That plus 2 implies we're giving up 2 electrons. Hydrogen doesn't have 2 electrons to give up. So this is not possible, right? Even though it works out mathematically, it's not possible because hydrogen only has 1 electron to give up. It can't become a plus 2. So that's why that doesn't work out. So a little bit of your atomic structure knowledge is going to help you out here. So this is the correct answer. So when you're dealing with peroxides, oxygen is going to be minus 1. So H becomes plus 1, and then it works out to 0 because now H can give up the 1. So oxygen's the one that adjusts. So here we're dealing with 2 usuallys according to our rules. So you got to have a little bit more knowledge about that. So don't forget this. You're going to see this again. Okay. So now let's move into today's lesson. So now we're going to get into the reactions. So we learned how to assign oxidation numbers. So that's what's going to help us move forward and get a little bit more information out of these reactions. So oxidation and reduction. So now we'll get into some more definitions. So often you'll hear me refer to these as redox reactions. So redox is just an abbreviation. It's a contraction of reduction and oxidation. So we can combine those two words because these two processes are always going to happen together. So they're never going to happen alone. So we can make this contraction and say redox. So what's going on here? In a redox reaction, there is a loss and a gain of electrons by atoms or ions. So again, take down these notes here. I forgot to mention that. And follow along with me as we go through the lesson. There's no fill-in notes here. So just write these notes in your notebook, on a piece of paper, on a tablet, whatever. So what's going on in an oxidation-reduction reaction? There's a loss and a gain of electrons by atoms or ions. So there's a loss and a gain of electrons, always. So oxidation is a loss of electrons. So oxidation is when we're losing. So we're losing electrons, and we'll talk about what that means as we go forward. So remember what it means to lose electrons. Electrons are negatively charged particles. So if you lose electrons, what happens? You become more positive. So your oxidation number goes up. You become more positive. So your oxidation number increases. So remember how we did this when we were talking about becoming ions. If I have, say, three protons and three electrons, when I become as a neutral atom, so when I become an ion and I lose an electron, now I have more positives. So when you lose electrons, you become more positive because you're losing negatively charged particles. If I lose another electron, now I become even more positive. Right? So the more electrons you lose, the more positive you become. Okay? So, and now going the other direction, reduction, that is a gain of electrons. Right? So a gain of electrons by an atom or an ion. So why do we call it reduce? Why do we call something where we're gaining a reduction? Because think about what's going on. You're gaining negatively charged particles, so your oxidation number is going to go down. It's going to become more negative. So again, we've done this before. So let's go back to my neutral atom. So now if I gain an electron, now I have one more electron than protons. My oxidation number is going to go down. Now it would be -1. I gain another electron, -2, right? So think about it directionally, and we'll talk about that more in a minute, right? And also the other thing you want to remember is the oxidation reduction reactions must occur together, right? So they always happen at the same time. So there's a loss and a gain happening at the same time. So think about the electron as like a baseball or a football. If you're playing catch, right, somebody throws the ball and then somebody on the other end receives the ball. All right. If there's only one person, you're not really going to have much of a catch. It's pretty sad. So the two must occur together. All right. So oxidation and reduction go hand in hand. That's why often we'll just call it redox. So how do we remember this? So here's a little saying to help you out. Leo the lion says grr. All right. So Leo says grr. So what do these things mean? The silly saying is going to help you out a lot in this unit. So Leo, what does Leo mean? A loss of electrons is oxidation. So losing is oxidation. So that's what you want to remember. And this is going to help you out here, Leo. And then grr, where does the grr come in? A gain of electrons is reduction, right? So Leo says grr is going to help you out a lot throughout this unit. So keep saying that. I'll keep writing it, and that's going to help you remember that losing is oxidation, gaining is reduction. Okay? And another thing that might help you out is Leo jumps up. So what does Leo jumps up mean? So Leo is very active here. So when you lose electrons, this is just reminding you that your oxidation state goes up. So let's think about if we had like a little number line here. So here's 0. All right. So just think about kind of where you are. All right. So if I'm here, right, if I'm at 0, right, if I'm at 0 and I lose electrons, so now if I lose one electron, I'm going to go to +1. I lose another electron, I'm going to go to +2. I lose another electron, I'm going to go to +3. When you're losing electrons, you're jumping up. You're becoming more positive. You're going in the upward direction, right? Even if I'm down here, if I'm at -2 and I lose one electron, I go to -1. So even though I didn't become positive, I'm going in the positive direction. So when you're losing electrons, you're jumping up, you're moving upward. So sometimes thinking about the number line will help you out. And also, same thing in the other direction, right? If I'm at +2, and I gain an electron, now I'm at +1. If I gain another electron, now I'm at 0. I gain another electron, now I'm at -1. Right? So when you gain electrons, you're being reduced. You're getting smaller. You're going down. Right? So that's why we call it gain reduction, because your oxidation state is going down. It's reducing. It's getting smaller. So sometimes this might help put things into perspective for you. So now keep this in mind. Leo jumps up. I'm going to leave those up here on the top of the screen to help you out as we're going through this stuff here. All right? So let's look at an example. So you might have heard the term oxidation before, like if I leave something out and it rusts, a piece of iron. So that's kind of the same thing that's going on. When iron reacts with air and the oxygen, you get iron oxide, which is rust. So it's kind of similar to this reaction here that we're using as an example. So if I just used iron instead of magnesium, that would give us our iron oxide. It's a different ratio of atoms in the compound, but ultimately the same thing. So let's use this as our example here. Magnesium plus oxygen makes MgO. So I kind of like to break this down into steps. So maybe you want to jot this down and this might help you. So step 1, we want to assign oxidation numbers. All right, so that's step 1. Just go through and give every element an oxidation number. Step 2 is going to be to connect the only two elements that change. So whichever two elements had oxidation states that changed, and we'll talk about that in a second. Number 3, we want to determine our loss and gain. And then number 4, we want to determine who's oxidized and reduced. So these are our 4 steps, right? So kind of keep those in mind as you're going through this. So it's going to help you out. So go through the steps. All right. So step 1, assign oxidation numbers. So let's go through and give every element an oxidation number. So don't forget about our first rule. Uncombined elements get a 0. So you want to go through and put your zeros in. So do that first, right away. Otherwise, you're going to make mistakes and you're going to forget. Right? So Mg and O are all alone. They get zeros. So now for MgO, you got to make your little table, use what you know to figure out what you don't know, what you need to add up to 0. So we know oxygen and we know magnesium here. So this is just kind of an exercise in going through the steps. So Mg is +2, oxygen is -2. So you'll get to the point where you might not even have to make the table. You can just do it in your head quick and figure them out. All right. So that was step 1, assign oxidation numbers. Step 2, connect the 2 elements that changed. So what do I mean by change? Well, here's our reaction arrow. So from the left side to the right side, the oxidation number changed. So here, magnesium 0. Over here, it's +2. So Mg changed. All right. Oxygen was 0 over here. It's -2 over here. So oxygen also changed. So ultimately, what we want to figure out is who is oxidized and who is reduced. So we're going to do that by first assigning oxidation states, connecting the elements that changed, and now step 3, determine the loss and the gain. So Mg went from 0 to +2. So this is where you're going to use your Leo says grr and your Leo jumps up here. So Leo jumps up. So whoever went up in oxidation state lost. So Mg went up. It went from 0 to +2. So that's going in the upward direction. So magnesium lost how many electrons? 2 electrons. How do I know 2? Because it's changing by 2 units. All right. So write that right over this connection that you made between the elements. All right. So, and write the number too. That's not really going to help us much out now, but it's setting you up to make the next step to the next part of this unit, and it's making that a little bit easier for you. So write this in now, because that's going to make a transition a little bit easier as we move forward. So magnesium lost 2 electrons. Oxygen went from 0 to -2. It went down. So that means it gained electrons, because we're gaining negatives and becoming more negative. So once you do this, that's the hard work. So now you're just going to use this to figure out who's oxidized and who's reduced. How are we going to do that? Using our Leo says Ger, right? Loss of electrons is oxidation. So whoever lost was oxidized. So who lost 2 electrons? Mg. Right? Now, we don't just want to write Mg. We want to include the oxidation state, because there's also Mg plus 2 over here. So we got to be specific. So Mg0 is oxidized. And who is reduced? Who gained? Grr. Whoever gained is reduced. Oxygen. Oxygen 0. So because it's a Brinkelhoff, you can write it as O2. But the easiest thing to do is just to keep it as one atom. Keep everything as one atom. Even when we get to the next part of this unit, that's going to make things a lot easier for you. So just keep that in mind. You might see it written like this, but if you had to write it, this is always correct. That's always fine, and that's probably the easiest way to do it. So we don't just write O, we write O0. So we call this a species. All right, the species is the element and the oxidation number. So the regents will often say, like, which species. So that's what they mean when they say that, the element and its oxidation state. So don't forget this moving forward. You're going to see that term a lot. Now, who gets oxidized and reduced? Remember, this is a reaction. Here are your reactants, and here are your products. So the reaction occurs on this side. So whoever is gaining and losing electrons, they're always going to be reactants. They're always going to be off the left side. So when we're picking our oxidized and reduced species, just remember, they're always off the left-hand side. We're not going to pick anybody on the right. It's always going to be on the left. So that should help make things a little bit easier when you're choosing who's oxidized and who's reduced. So who lost? Mg0, which means it was oxidized. Who gained? O0, which means it was reduced. So remember that Leo says grr. So let's try another example. So copy this down, and we'll go through it. So remember the 4 steps that we wrote out on the last slide. Step 1, assign oxidation numbers to everybody. And even when you first start that, uncombined elements get a 0. So whoever's all alone, so take a look and see, okay, who's all alone? Oh, Cu's all alone. Let me give that a 0 right away before I forget. Now everybody else, we got to go through and figure it out. All right, so make your little table if you have to. Use what you know to figure out what you don't know. So I know oxygen is -2. There's only one oxygen, so the total is -2. So I need a +2 over here. There's only one copper, so it gets the entire +2. All right, so move on to the next one. Again, I know oxygen is -2, so carbon must be +2. Over here, same thing, but now oxygen is -4. Because there's 2 oxygens, don't forget to multiply by your subscripts. So now carbon gets the +4. That's step 1. Once every element has an oxidation state, then you can move on to step 2, which is connecting the 2 elements that changed. Only 2 guys are going to change. So who changed here? Well, let's look. All right, now by changed, what do I mean? You got to look from the left to the right. All right, from the left to the right. So you're not looking at elements on the same side of the reaction. So I'm not saying, oh, oxygen's going from here to here. I got to compare the oxygen on this side to the oxygen on this side. And it doesn't change, so oxygen doesn't matter. So copper goes from +2 to 0, and carbon goes from +2 to +4. So those guys changed. Now, oxygen didn't change, so we don't really care about oxygen here. Only 2 things are going to change. So once you figure out who changed, those are the 2 things you want to focus on. Everybody else at that point doesn't really matter. All right? So now, remember, Leo jumps up. Whoever lost electrons is oxidized. Leo, right? Remember your Leo says Ger. And whoever gains is reduced. So now Leo jumps up. So whoever lost electrons went up in oxidation state. So copper went from +2 to 0. Think about your number line. Which way are we going? That's going down. So that's gaining. Carbon went from +2 to +4. That's going up, right? Leo jumps up. So that means we're losing loss of electrons. The oxidation state is going up. We're becoming more positive. So sometimes it helps to do your loss first. Say, okay, who lost? Who jumped up? Carbon went from +2 to +4. So that's a loss of electrons. So we're changing by 2 units, so that's 2 electrons. Copper went from +2 to 0, so that's a gain. So it went down. So once you get your loss and gain, you're in pretty good shape. So that was step 3, figure out who lost and who gained. And now step 4, who's oxidized and who's reduced. And remember, they're always reactants. They're always off of the left side of the reaction. So and this is where you want to use your Leo says Ger. So you say, okay, who lost? Carbon +2 lost. So Leo, that means it was oxidized. So carbon +2 is oxidized. Who gained? Copper. Copper +2 gained 2 electrons. So Ger, that means it was reduced. We're done. That's it. Once you tell me who the oxidized and reduced species are, right? Remember, these are our species, element and oxidation state. You're done. So who's oxidized, who's reduced? So if you can figure that out, then you're in good shape, and it's a good place to wrap things up for today, but we still want to practice before we finish up completely. So the other thing, though, you want to be able to do is to determine if you're dealing with the redox reaction. So not every chemical reaction is a redox reaction. So how do you identify a redox reaction? So the easy way to do it is if an uncombined element is present, so uncombined meaning an element all alone in its elemental state. If there's at least one uncombined element in the reaction, then it's a redox reaction. That's kind of a little trick to remember that you're dealing with a redox reaction. So if you see at least one uncombined element, then it's a redox reaction. Because what's that going to show us? That's going to show us there's a change in oxidation states. All right. So if there's no change in oxidation states, it's not a redox reaction. So sometimes you have a reaction, but no oxidation states change. So this is a quick and easy trick to help you identify it right away. If you see at least an uncombined element, at least one uncombined element. So see copper all alone, it's a redox reaction. So let's look at some practice problems. So take a look at this. I have the worksheet attached to this lesson. Let's try these out together. So now before we go through and figure out who's oxidized and reduced, first thing we want to do is say which ones are redox reactions and which ones aren't. So what's the quick and easy way to do it? Is there at least one uncombined element? So number 1, zinc and copper. Those are 2 uncombined elements. They're all alone. So that's definitely a redox reaction. So we'll put a little check next to that. That one's good. Next one. All right, I see a bunch of compounds here, but I don't see any uncombined elements. So this is not a redox reaction. So why not? Because if I actually sat down and went through and assigned oxidation numbers to everybody, and I'll do that quick for you. Now notice, look at these oxidation numbers. Nobody's changing. Sodium's +1, +1. Chlorine's -1, -1. Magnesium's +2, +2. Bromine's -1, -1. Nobody changed. So that's why this is not a redox reaction, because there's no change in oxidation states. All right? There's no change in oxidation states. There's no movement of electrons. So not every reaction is a redox reaction. So if there's no movement in electrons, it's not a redox reaction. So quick and easy way to tell that, look for at least one uncombined element. So number 3, calcium and aluminum. Those are uncombined, so that's a redox. Now number 4 is a little tricky. Remember, uncombined elements are neutral. So even though sodium and chlorine are alone here, they have charges. So these are ions. Don't forget about your ions. Ions are not uncombined elements, right? They've gained or lost electrons, and now they have a charge. So there are no uncombined elements in this reaction. So this is not a redox reaction. And again, if we assign oxidation states, remember, ions, your charge is your oxidation state. So +1, -1. Over here in our compound, +1, -1. Nobody's changing. Okay? So we don't have to do anything with those. So now number 5 is also a redox reaction. How do we know? Uncombined element. Lead's all alone, copper's all alone. Right? Now these guys are ions. So they're not uncombined, but these two are. So this is a different kind of a reaction here. They're not really showing you the whole picture here. They're making it easier for you, actually. So copper and lead, these ions are bonded to somebody, but they're not showing us that ion that they're bonded to because its oxidation state isn't changing. So they're kind of taking it out of the equation and just showing you the ones who are changing. So they're making things easier for you. All right. So say this were like, say it were, I don't know, bromine, CuBr2, right? Then copper would be +2, bromine is -1. And then if this one were PbBr2, right? +2, -1. So you notice bromine's oxidation state isn't changing. So we call bromine a spectator ion. We call that a spectator ion. It's just watching, right? It's not involved in that movement of electrons. So just like a spectator at like a sporting event, it's just watching, right? It's not involved in the game, it's just watching. So the spectator ions, their oxidation states don't change. They're just kind of watching the movement of electrons take place, right? So now we've identified the ones that are redox reactions, 1, 3, and 5. So for 2 and 4, we don't have to do anything with. So now let's go through 1, 3, and 5, and I want you to go through all the 4 steps that we did before. So, and you're ultimately going to end up telling me who's oxidized and who's reduced. So if you can get to that point, you're doing great. So pause the video, try these 3 problems out, go through the 4 steps, assign oxidation states, connect the 2 elements that changed, who lost, who gained, and then who's oxidized, who's reduced. Right after you've done those, unpause it and we'll go through it. So if you're a little confused still at this point, then let's work through the first one together, and then you can pause it and try the other 2 and so on. So if you get stuck at any point, just kind of go forward and then pause it and try and do it. But try and do as much as you can on your own here. But if you're stuck on number 1, unpause the video and see how we work through it together. So step 1. Assign oxidation states. So remember, put your zeros in right away. So who's all alone? Zinc and copper. So let's give them zeros. So now for CuCl2 and zinc Cl2. So now for CuCl2, copper has more than one oxidation state. So we don't know that. But now chlorine, remember, we didn't really have a primary rule for it, but we did have kind of a secondary rule for it, where it's a halogen, a group 17. So when they're on the end of the compound, like it is here, they're going to be -1. So just like fluorine, but they're not always -1, but they are when they're on the end. So we can use that here to help us out. So -1 times 2 is -2. So then copper is going to get the +2 because that's what we need to equal 0, right? And then the same thing over here. But we know zinc is +2. We know chlorine -1. So whatever, you figure those out. So step 1, assign oxidation states. Step 2, connect the elements that changed. So zinc went from 0 to +2, and copper went from +2 to 0. So those 2 changed. So chlorine didn't change. So chlorine we would call our spectator ion, right? It's not involved in the movement of electrons. It's just hanging out and watching the show. So next up, who lost and who gained? So remember, sometimes it's easier to say Leo jumps up. Whoever went up in oxidation state is the one that lost. So zinc went from 0 to +2. So that went up. So that means we lost 2 electrons. Copper went from +2 to 0. So it went down because it gained negatively charged particles. So that's what you want to make sure you get right, the loss and the gain. So you're losing, your oxidation state goes up, Leo jumps up. And when you're gaining, your oxidation state goes down because remember, you're losing and gaining negatively charged particles. So you lose negatives, become more positive. Gain negatives, you become more negative. All right, so now that was the hard part. So now all we want to do is use our good old Leo says grr to figure out who's oxidized and who's reduced. So whoever lost is oxidized. So who lost? Zinc 0. And then whoever gained is reduced. So who is reduced? Copper +2. So remember, we want our species. Don't forget that. The element and the oxidation state. So don't just write zinc and copper. Zinc 0 and copper +2. And where are they always off of? The left side. They're always reactants, right? So now let's try number 3. Remember, 2 and 4, we're not doing anything for because they're not redox reactions. So step 1, assign oxidation states. Uncombines, get a 0. Go through your other elements, make your little table if you have to. And there you go. Then we connect the ones that changed. So calcium, aluminum changed. Calcium went from 0 to +2. So where are we going? We're going upward direction. So that means we lost, right? Leo jumps up. And aluminum went from +3 to 0. So that's a gain of 3 electrons. So Leo says grr. Ca0 lost, so it was oxidized. And Al +3 gained, so it was reduced. And remember, we're always off the left side. This is your loss and gain. That's that movement of electrons. So calcium is losing those electrons and aluminum is gaining those electrons. So that's that movement of electrons that's taking place in a redox reaction, right? There's always a movement of electrons. And then the last one is easy, right? They took the spectator ion out of the equation here. So put your zeros in for your uncombined. So now lead is going from 0 to +2 and copper is going from +2 to 0, right? Those are the only 2 elements in the equation, and they're both changing because, like I said, they made this easier by removing the elements that aren't changing. So lead lost because it went up, right? Leo jumps up, and copper gained 2 electrons. So Leo says grr, Pb0 lost, so it was oxidized, and copper +2 gained, so it was reduced. All right, and that's it. So if you can go through and do all this and tell me who's oxidized and who's reduced, then you're in great shape and you're in a good position to move forward in this unit to the next step where we just kind of expand upon determining who's oxidized and reduced and build upon that. So that's it for today. I'll see you next time.